last time we started talking about reductions, and reductions allow you to more easily prove that additional languages are undecidable or unrecognizable. I showed you also a language that was unrecognizable last time, right? It was the co-ATM, right? I think, yeah. So then we started talking about reductions. So we said A reduces to B. So A is a language and B is a language. What that means is that we can use any decider for B to decide A. Okay? So on the assumption that you have a decider or a recognizer, but let's just say decider right now, decider for B, okay, whenever you have an instance of language A, you have a string and you want to know, is it in language A, you can do something. So you have a string W and you want to decide if W is contained in A. So you do something to create some input, let's call it W prime, to language B. And then you decide whether W prime is in B, because you have a decider, and based on that you accept or reject. Okay? But we really want a decider for A, and so this has to be, what you fed to B has to be of the form so that this is input W to language, or to the question of whether it's in language A. So W comes in. This is the transformation or the reduction that happens here that takes W and does something to create another input W prime, which is input form for B. B decides is W prime, the decider for B decides whether W prime is in B, and accept reject, but that accept reject has the meaning of whether W is in A. Okay? All right, so that's a review of what it means to reduce language A to language B. Okay? So then we have some simple consequences. We talked about these last time, but we didn't exploit them. If A is reducible, reducible to B, and B is decidable, then what? I'm just going to stand here until somebody answers.
Then A is decidable.
Then what?
A is decidable.
Yeah, right. I mean, this is really just a rewriting of what this picture says, okay? And then A is decidable. Okay? This is just saying what this picture said. I mean, so it's in a sense just, encapsulating it in a kind of more succinct, terse way. Okay. If A is reducible to B and B is undecidable, nope. A is undecidable, then what? Well, we talked about this last time, but just think it through. And B is undecidable. Undecidable. Yeah, undecidable. I can't spell it, so I'll just say UD, undecidable. So yeah, if A is reducible to B, if we know that A is undecidable, there's no possible Turing machine that can decide A. And yet we have this mechanism that can convert any instance W of the question of whether or not W is in language A. We have a way of reducing that to language B, which means that a decider for B could be used to decide A. But A is undecidable. So it must be that B is also undecidable. There can't possibly be a Turing machine that can decide B, because with that Turing machine that can decide B, we could decide A, but A is undecidable. Okay? So this is, yeah?
I have a question about reducibility in general.
Yeah.
If A is reducible to B, then does it follow that B is also reducible to A?
No. Yeah, it's not necessarily symmetric. There are whole classes that are symmetric, and we'll be talking about them. But definitely, it's not true in general that just because A is reducible to B, that B is reducible to A. Okay, let me give you a third one here. If A is reducible to B, and B is undecidable, then what? Then what?
We don't know.
Yeah. Here I was hoping that nobody would answer, and I would say, that's the right answer. Yeah, this means nothing. Okay, then, okay, so it is. But so what? Doesn't really mean anything. I mean, it can certainly happen that A is reducible to B and B is undecidable, and, okay. All right, good. Good answer. All right, so we're going to exploit this one, though. Okay. We're going to exploit this to prove that additional languages are undecidable. And each one of those languages that we show to be undecidable, we could prove by a self-reference argument or by diagonalization. You can go back and use those basic proof techniques, but it's easier once you build up a repertoire of languages that you already know are undecidable or unrecognizable, then you can, well, here we're just talking about decidable. When you build up a repertoire of languages that you know are undecidable, then you can use this idea to prove that additional languages are undecidable. So if we already know that A is undecidable and we want to prove that B is undecidable, what we want to do is come up with a reduction that shows how to reduce A to B. That's the game plan. If we know A is undecidable, and we want to show B is undecidable, we should, or one approach that will do that proof, exhibit a way to reduce A to B. And then based on this idea, that will establish that B is undecidable. Okay? Okay, so let me do some. Here's a language. Okay? So the strings in this language have the form M, comma W, a Turing machine, description of a Turing machine, and input W, such that M is a Turing machine and M halts when it's given W. Now, how does this differ, by the way, from ATM? Looks very similar to ATM. Do we still have ATM up on the board there? Yeah, it does. We have ATM all the way on this board. Okay? So, well, except for the fact that I have this confusion about when we need those. I have this confusion about when I need these extra little marks, but so anyway, I want this to be the same input, MW. So what this is intended to mean is it's a description of the Turing machine M, and then followed by a particular input W. M is a Turing machine, and M accepts W. Okay? So how does this differ from halt? Yeah.
Over here, M is a recognizer, over here, M is a decider.
I only heard a few of those words. It didn't sound like the right ones, though.
On the left,
Yeah.
M is a recognizer, or over here, M is a decider.
No. So the suggestion is this is a recognizer and this is a decider. But in fact, this is that's just not right. Yeah.
Halt TM accepts when M rejects W also?
That is true. Is that the crucial difference? Yeah, I guess so. Okay. All right. The answer I was looking for is that this is just deciding whether or not M is going to halt. Now, when it halts, either accepts or rejects. Okay. So this will also say yes, it halts when M rejects W, and that was your suggestion here. But the key point is that I want to say this decides whether M halts, whereas in ATM, we're looking for a Turing machine that accepts only when M accepts. Okay, so but it would reject when M does not accept. Okay, so it would reject if M either rejects or if M doesn't halt. Okay, but the key difference is this one is deciding. This language it would be decided by a Turing machine that is concerned with whether or not M accepts W, and over here, this language is accepted. This language is decided by a Turing machine which is concerned with whether M halts on W. Okay? All right, so they are different, even though they have a certain superficial relationship. Now, we know that ATM is undecidable, and we want to prove that this language halt is undecidable. So in terms of this logic, which language plays the role of A and which language plays the role of B? Yeah, ATM plays the role of A, and therefore halt plays the role of B. So in this example, ATM plays A, and halt TM plays B. Okay. Well, what that means is that we have to explain how we're going to use a decider for halt TM to decide ATM. Okay? We need to show how a decider for halt TM could be used to decide ATM. Okay? Now, what names do I want to give to these things? A decider R for ATM, for halt TM, could be used to decide ATM, that is, build a decider H for ATM. Okay? So the way this is going is we're assuming that we have a decider for halt. It's called R. It's a Turing machine R, which decides this language halt. And we want to show that using that decider R, we could build a decider H for ATM. And that, if I can do this, I've shown that ATM reduces to halt. And because ATM is undecidable, therefore halt TM must be undecidable. Okay, so how do we do this? So, yeah, we're going to keep that. Anybody have an idea? Okay, so I'm trying to build H. First of all, H is supposed to be a decider for ATM. So what's the form of its input? What's the form of input to language ATM? Or to any decider for language ATM? Anybody take the hint? Okay, ATM, the input consists of this pair, a description of a Turing machine and input W to that Turing machine. So MW. Okay? Now inside H, we're going to have a copy of R, right? Because we're trying to use R. We're trying to use the supposed existence of R, Turing machine R, to build this Turing machine H, which is a decider, which will be a decider for ATM. H is a decider for ATM. And so inside it, it has an R, which is the magic that's going to make H possible. Because we know there is no such H. ATM is undecidable. But now we're doing this thought experiment called a proof, or this proof that involves this thought experiment. Suppose this Turing machine R exists, which is a decider for halt. Okay? So anybody have an idea of what R should do? What is that? TM. I mean, it's like that Intel inside, that you have on your computers. H has R inside. And so what should R do when this input comes in? Yeah.
You Turing machine will run the decider for halt TM on the same input that it gets. And if that rejects, then you know that it's not going to halt. And so you can just flat out reject and say that like the original Turing machine wouldn't accept.
Yeah.
But if the halting decider accepts, then you can just simulate the original Turing machine on the input and then do whatever that does.
Exactly. That's exactly it. So R takes in MW, and what does R do? It either accepts, which really means that M halts on W. Actually, I want to write this, give myself some room. Except, it means that M halts on W, or it rejects, which means that M does not halt on W. Well, if M doesn't halt on W, it certainly doesn't accept W. If M doesn't halt on W, M certainly doesn't accept W, right? So this reject should translate into a reject out here, okay? This is the outside of H. This is the outside of R. This is R and its outside. So reject from R should mean a reject from H, okay? Accept from R means that, yes, M will halt if it's looking at W. So if M halts when it's looking at W, it's either halts with an accept or a reject, okay? If M halts with an accept, then the output here should be accept. If M halts with a reject, then the output should be reject. Now how does H, at this point, having used R, it only knows that M halts on W. It doesn't know whether M halts with an accept or M halts with a reject. So what's the rest of the piece inside of H? We heard the answer. Who can tell me again that part of it? You look like you're ready to answer. Yeah.
So then you feed the string MW to ATM and see whether or not it accepts?
No, sorry. What?
Universal Turing machine?
Universal Turing machine, that's a good... Then what does the universal Turing machine do?
It's a recognizer.
Anybody else? Okay, so when this happens, then inside H, we could have a universal Turing machine that simulates M on W. Okay, remember, universal Turing machines can take in a description of a Turing machine, some other Turing machine, and input to that Turing machine, and it can simulate that Turing machine on that particular input. Okay? And this simulation will do exactly what M would do on input W. Now, there's no worry that M might not halt, because we've already decided here that yes, M will halt on input W. So we can do the simulation until M halts, and M is going to halt either with an accept or reject. So if this simulation is a reject, that is, it finds that M rejects W, then out comes a reject. We have two possible reject states, no big deal. But if it finds that M accepts W, M accepts W, then this is an accept. Okay? Now this is a decider. This is a decider for ATM because it always ends with reject or accept. It never gets into a state where it goes forever. So in comes MW, and out comes, yes, M accepts W, or no, M does not accept W. That makes this, H, a decider for ATM. But we know there is no decider for ATM. So what made this possible were these two pieces. Okay, this piece does exist. Universal Turing machines exist. So that's not the cause of the contradiction. But this was the assumption that there was a decider for R. Okay, and we've shown if there's a decider for R, then there's a decider for H. But we know there's no decider for H, therefore there's no decider for R. Therefore, halt is undecidable. Okay. Halt TM is undecidable. UD. How many people feel like you're getting this? Oh, good. A quarter of the class. Okay. How many people have taken classes that have these clickers? There's something called clicker technology. What does that do? Does that just tell, you can stop and ask how many people understand this? Okay, so we didn't need to have a clicker here. This is like the Turing machine version of those clickers. I mean, the clicker is a little more high technology, but we're doing the same thing here. We're simulating it by just stopping and asking. Okay. All right, but study this in the book, and the book has many other examples of reductions. I want to show you another example. We'll just keep doing them until the time runs out today. There are a couple more from the book that I'll show you if we have time. But I want to show you one that is similar to a problem you have on your homework. Okay, by the way, how many people have looked at your, there's another clicker question. How many people have looked at your homework that's current? Okay. All right, so you've noticed that I had a couple of changes of heart. One is well, maybe you didn't because that was within the first 20 minutes of posting it. I extended the time that you're allowed for this homework, so take a look at that. Just in thinking about the schedules and Thanksgiving, and I decided this one should have a little bit more time. Not a whole lot more, but a little bit more time. And the second thing is that in the original version, I put a problem on it that later I decided was too hard, and so I did a substitution of problems. So that happened within half a day of the first posting. So probably most of you never looked at the first version, but in case you did look at it quickly and you don't see a discussion there that I've changed one of the problems, look again. Okay, so one of the problems that I put on in the second round is the following. This is actually a question out of the book. I think it's 5.9, which is to look at the following language, and I don't remember what it's called. We'll just make up a name for it. A reverse. Okay, so I don't know whether that's the right. It's probably not. M such that M accepts W if and only if M accepts W reverse. Okay. So this is saying that M is a Turing machine, and we want to know, does it have the behavior that whenever it accepts W, a string W, it accepts W reverse. And of course that's symmetric because the reverse of a string, the reverse of reverse is the string itself. Okay? So some Turing machines have that property, some Turing machines don't have that property, right? We want to know, is this language decidable? That means, is there a Turing machine which can take in a description of another Turing machine and decide whether or not M accepts whatever string it accepts, it will necessarily accept the reverse. Okay? Now again, this is a question about an infinite set of strings. So we can't, you can't build a Turing machine which simulates M and then just tries all the different inputs. You could build a simulator for M and feed it W and see if it accepts it, and then feed it W reverse and see if it accepts it. And if you ever get to a point where it has a W that it accepts and the reverse it doesn't accept, then you can reject. But what if, in fact, M has the property that it accepts W if and only if it accepts its reverse? Then every time you feed it W and it accepts, you'll feed it W reverse, it'll accept, and you'll never know when to halt, right? So that's why it's a problem. You have to actually prove through reductions that that A rev is undecidable. Okay? But does everybody see the context of the problem? We want to know if there's a Turing machine that can take an input of that type and decide whether or not whenever M accepts a W, M would also accept W reverse. Okay? So, of course, I'm not going to show you how to do that because that's on your homework. All right, but I want to show you a similar problem. A circ M such that when M accepts, so M accepts W if and only if M accepts a circular rotation of W by one place. Okay, what do I mean by a circular rotation? So maybe W is ABC. A circular rotation, let's say to the right, circular rotation of W by one place to the right. Okay, so that is CBA. No, CAB, sorry. CAB. Okay, so we just circularly rotated, and you have CAB. Okay? So you can have Turing machines that accept a particular language. The Turing machine recognizes a particular language. And it happens to be that whenever a string W is in that language, so is the string which is one circular rotation from that W. Okay? Which, by the way, implies that all circular rotations would be in W, would be in the language, right? Because this is circular rotation by one position, but then if this is also in the language, one W circulating, one circular rotation from that is BCA, and one circular rotation from that is back to ABC. Okay, so this is really, I could have rewritten this as M accepts W if and only if M accepts all circular rotations of W. Okay? All right. So I want to know whether this language is decidable. All right. That a circ is undecidable. Okay? So this is going to be a reduction, and so we have a repertoire of languages that we already know are undecidable. We know that ATM is undecidable, and we know that a halt is undecidable. Now we have a repertoire of two languages. So either one of those can play the role of A. This plays the role of B. And in doing these kinds of reduction proofs, it's really a matter of judgment which language you use for A. Sometimes some languages make it very easy to do the reduction if they're used as A, and sometimes other languages make it very hard. But so, and I'm not claiming that this is the best choice. I'm going to use ATM. I reduce the known undecidable problem to 2, the problem that we're trying to prove is undecidable. Okay? And as I mentioned last time, lots of people get this backwards. I've even seen it published by professional computer scientists sometimes where they got it backwards and proved exactly the wrong thing. And somehow it went, it escaped the reviewers, and it's anyway. I've certainly got it wrong at times. I never published one, but at any rate. So we'll reduce ATM to a circ. So we assume we have a Turing machine R that decides a circ, and we want to show, therefore, a Turing machine H that decides ATM. Okay. So I'm stalling for time because I didn't write this down. It was so clear to me that, why bother? But now that everybody's looking at me and the TV at home, let's see if I can do it. Okay. So this is my H, and of course inside it is going to have R, and we're going to use R as the crucial magic to make H work. So what's the input to H? H is supposed to be decider for ATM. So what does the input to H look like? It's what? I couldn't hear it.
A machine in the string?
Yeah, a machine in a string. Good. Okay, good. Now that's what comes into here, and ultimately we want accept or reject. Okay, so now we do have this decider R for circular rotations. Okay, and the crucial thing here is that we have W as a specific input. So in here is a machine and a particular W. In the language ATM, we want to know whether M accepts W. And if this is a decider, M accepts W or not. Okay? So we have the particular W. And this is a machine here that can decide a circ. Okay, so what is going to happen in here? I haven't quite left myself enough room. So here, I'll just make R smaller. R decides a circ. What's going to happen inside here is we're going to create a new Turing machine, or description of a Turing machine. Given M and given W, we're going to create a description of another Turing machine. And that other Turing machine is going to be given to R. So this will be Turing machine M, I'll call it MW. Okay, so it's got something to do with M, and it's got something to do with W, but it's not the same as these two. And so what is MW? That's a Turing machine which is supposed to do the following thing. It's a Turing machine which on input looks at its input and decides, first of all, is its input W? Or is its input, and it needs to also decide if its input is one circular shift of W. Okay? Can we build inside here a Turing machine that can look at MW and decide whether the input is specifically W or not? Now, I'm saying this wrong. Inside here, we need to, that is H, takes in, H is the decider for ATM. H takes in that input, MW. Now, M and W exist. They exist at this point. They're real input. So what H does is it looks at that and creates the description of a Turing machine, which I'll call MW, that does a few things. Okay, so I need some more room here. I want MW is a Turing machine that takes in some Turing machine. No, sorry. Sorry. It takes in W. It takes in some input. I'll call it W prime, and decides if W prime equals W. Okay? So again, at this point in the construction, H has the specific Turing machine M, and it has a specific input W. And so it's now going to create a Turing machine, which the first thing it does is can look at any particular input. It can take in any particular input W prime and decide if W is equal to W prime. Okay? Well, that's easy. I mean, we even can build a finite state machine that can, if we already know W, if we actually do know W, we can even build a finite state machine that recognizes whether a string W prime is W. It doesn't even have to be a Turing machine. And it can also decide if W prime is equal to W rotated, or what do I call it over here? Rotated or circular? Yeah, rotated. Right, by one place. Okay? So that is what MW, that's the first thing that MW is supposed to do. It's supposed to just look at whatever input it gets. It's supposed to be a Turing machine that can take in input. And it's supposed to look at its input and decide whether that input is W or W rotated one position. Okay? If the input W prime is W rotated one place, then MW accepts. Right? I say right, but obviously nobody can know whether that's the right thing yet because you haven't seen the big picture. If input W prime is W rotated one place, then what MW shall do is accept. If input W prime is not W or W rotated, then MW rejects. Okay? So those are the two things that MW does. Now, again, remember the context. In comes a description of a Turing machine M and a string W. And inside H has to be a Turing machine that can create a description of MW. Does that sound doable by a Turing machine? Yeah, it's got the W here. So it can certainly describe, even as I was saying, you can even describe a finite state machine that will look at W prime and take the following actions. Okay? So I have what MW should do when W prime is rotated one place, and what W prime should do when what MW should do when W prime is not W or W one place. So what's left out is what should MW do when the input is W. Okay? If the input is if the input W prime equals W, then MW simulates M on input W. Okay? So MW is a Turing machine which is already had pre-knowledge of this input string W. It's built into it. And then when it's fed an input W prime, it checks whether that input W prime is W or W circulated or something, neither W nor W circulated. If it's neither W nor W circulated, it just immediately rejects. Okay? But if it's W circulated by 1, immediately accepts. But if it's W, then what it does is it simulates M on input W. And where it knows M, because M was input here, H takes in that input and creates a description of MW. And so again, can H create a description of the MW which can simulate M? Sure. It just has within it essentially the description of a universal Turing machine. And that universal Turing machine is going to have it's just going to be specialized so that when it sees, well, it's basically a universal Turing machine which takes in M and knows how to simulate M because it's a universal Turing machine, and then it takes in W, and the universal Turing machine does that simulation of M on W. So all I'm saying here is that this part exists. H can take in MW and H can take M and W and create this description of this Turing machine MW, and here is a complete description of what we want MW to be. Okay, having done that, the output of this is a description of MW. It's sitting on some tape. H has a tape, and after it does all this, what is sitting on that tape is a description of MW. Right? Now, what's R? It's a Turing machine which can take in a description of a Turing machine and accept that Turing machine M if M accepts W, if and only if it accepts a circular rotation. Okay? Now this, any W, whereas this is a specific W. All right, so into R comes the description of MW. Now, MW, so we want R to decide whether MW, whenever it accepts a particular input string, it accepts its circular reverse or circular rotation. Okay? And the other way around. Whenever it accepts the circular rotation, it accepts the string. Well, MW rejects everything besides W and W circulated, right? So the only relevant strings to MW are W and W circulated. So, but it always accepts W circulated, right? So if R decides that MW, if R accepts MW, what does that mean? So this is the key thing that you have to see, that I want you to see. R accepts MW if and only if M accepts W. All right? So we have created or we have shown that H, we have shown that H can create MW so that R accepts MW if and only if M accepts W. Go through this step by step. If R accepts MW, okay, that means that MW is a Turing machine which has the property that whenever it accepts a particular input, for whatever particular input it accepts the circular rotation. But the only possible inputs that it can accept are this specific W or the circular rotation. It rejects everything else. And in fact, it accepts the circular rotation. So there's only one string where there's any question about whether MW accepts or rejects. Or there's only one relevant W to consider. So MW is a Turing machine where we reject almost all strings, we accept the circular rotation of W, and then if R says yes, MW is a type of a Turing machine that whenever it accepts an input, it accepts the one rotation of it, it means, or if and only if, it accepts an input if and only if it accepts the one rotation of it, that means that M accepts W. So accept over here means M accepts W. What does reject mean? Well, again, R is deciding whether MW is a type of Turing machine which accepts an input if and only if it accepts the circular rotation of an input, of that input. But we know that MW accepts this particular W circulated by one position, and it rejects everything that isn't W or that circular rotation. So the question of whether or not MW has that particular property is just the question of whether M accepts W. And so if it rejects, that means that M rejects W. That means that H is a decider for ATM, which means that ATM is decidable, but we know ATM is not decidable. So ATM is not decidable, so this R, this can't exist. Why can't it exist? Is it because of this part? No, we were arguing that this part is really possible, that you can take in an M and a W and the Turing machine in here could build this other Turing machine, MW. But, so it must be this that's the problem. This doesn't exist. So if R doesn't exist, then this language, a circ, is not decidable. Whew. Okay,